talk of this lecture series. The title, so.
Thank you. Well, if I had to choose a title, it would probably be something vague, like more about sheaves and high categories. So I want to begin by saying a little bit more about a construction which I talked about last time, and that is a way to get very easily full faithful embeddings of high categories when you have stops. So to remember the setup, so W will be right now Liouville manifold, and X will be a Liouville hypersurface inside the boundary of W, so it's X. X is a Liouville manifold. And then we have an embedding of X as hypersurface inside boundary infinity of W. So I can consider now the core X, or recall this is the core X, the stuff which doesn't escape to infinity. And I consider this inside the boundary infinity of W as a stop. And I'll also consider Cx plus, this is small grade push off. So when we're in this setting, we get full faithful embeddings. So proposition full faithful functors W of X into W of X plus T star 0, 1. Running out of space here. Let me put that as it. So it's just W of X goes into W stopped at Cx union union the positive. Okay, so I drew the proof of this last time. So we have here boundary infinity W. This here is W. Two copies of this dot here. Cx, let's make wrapping go counterclock in this direction. Cx plus, and now you have this embedding here. X cross T star 0, 1. Okay, and the map is simply you take a Lagrangian and you cross it with this curve. So this is sort of running out of space here. But call that curve gamma. The map is just L, maps to L cross gamma. So the reason this is fully faithful is simply, well, okay, so first you have the map from W of X into W of X cross T star 0, 1. That's the Kunith embedding that's always fully faithful. This is just L maps to L times the fiber. And then you have this map from here into here. That's fully faithful because these two cores, they completely stop the wrap once something exits. Okay, so the boundary infinity of this guy has an exit set that has a union of two copies of X. And you, with these stops here, just Lagrangians, once they leave, they just immediately hit the stop. Okay, so one can do the same thing.
Can I ask a question?
Yes.
Can you give us a picture? So where does the red flow on the boundary of X happen under this embedding?
On the boundary.
Because it's a wrap pattern of X. Right?
Yes. Yeah. Somehow. In this picture, I guess it would be somehow at the fibers over this picture are non-compact, and so it happens in the fibers. Yeah. Great, so let's do the same thing with the stop. So let's say F inside infinity X is a stop. I'd like to do the same thing. So in order to do the same thing, we're going to need some additional assumptions on X. So let's say this is a singular isotropic, and let's say X is Weinstein. That's an additional assumption. We'll want. Okay, so the first thing to say is what is the new stop? So somehow the stop that we use here has to take into account F somehow if we want to get a full faithful embedding of Wx, F into something. The goal is to get a full faithful embedding of Wx, F into W stop at something. Okay, so the first question is what is this? So I guess the easiest way to define it is just to draw a picture. So all right, let's look at half plane. This is a half plane cross X. So let's remember what is the boundary of infinity of this guy look like. So okay, so I've drawn just the base, and this is fibering over the picture of fiber X. So the boundary of infinity looks like the boundary of infinity of X across this base, union with this circle crossed with X. Right. Now, in fact, I'm going to use a slightly different Liouville vector field. So the Liouville vector field is 0 on segment. Now it's radial. Okay, using this Liouville vector field. So now I want to consider the following. Stop. So we put the core of X here. We put the core of X here. And over the segment, we put F cross R. Okay, so this defines stop, which I'll just we will write as core of X union positive push off union R cross F. So probably one should eventually figure out a better notation for this, but I'll just write it like this for now.
Sorry, why couldn't I have done it in this picture here, where I could have just put Cx and Cx plus, and then at infinity I can just put that F plus an interval between them?
You could. I was just
Okay.
well, this was sort of a more schematic picture.
Okay.
F doesn't lie in Cx or Cx plus. What's happening with these two?
Yeah. So if I just drew. So maybe I should just draw a picture. So X. So this is a picture X. Okay, so you have the core of X. Here, F lies at infinity, and of course the common thing to do when you do this relative skeleton picture, should use a different color, is you add this sort of, well, R cross F here. So in here you sort of have two copies of that. Here you have CX with F cross R coming down to it. Here you also have CX with F cross R coming down to it. And the two copies of F cross R are the same copy.
So the F cross R is using the Liouville flow on the base and on X at the same time?
Yes, yes.
Alternatively, you could probably just take F cross R without doing any Liouville things, and then in those fibers attach an extra cone over F.
Yeah, I understand. Which was the
Yeah. I mean, somehow it would, there's this formula for what is the product stop. If you take and this formula is sort of complicated, but really one should just say, what is the product core? And then it's easy. It's the product of the cores. Go ahead. So now, right. So I've defined for you this sort of composite stop inside the standard model. But now, if you have X as a Liouville hypersurface inside anything, inside any contact manifold, inside the boundary of infinity of W, then you get it has a sort of standard neighborhood, X across a half plane inside W, standard neighborhood result. And so using this, we can implant this stop in W. So using this, we get CX union CX plus union R cross F inside here. Okay, so now we have the same proposition. Okay, so now well, I've stated the assumptions there, but let me state them again because they're stronger than the assumptions right there. So here X now is Weinstein F singular isotropic. Then there's this well-faithful. First point is that now it's the stop category X comma F inside. So the stop. So eventually, I think we're going to have to give a geometric proof of this result. It's important for other things, but there's another proof of this result using Knuth and using the Meyer-Vietaris push-out that I discussed last time. I think that's a good.
Can you say why the conditions are stronger?
We're assuming X is Weinstein.
Yeah. Why are we assuming?
Oh, because it's needed for the proof I'm going to give.
Okay. I didn't know they were mumbling. Was that meant that you can give us the proof or not?
I'm going to give you the proof.
There's a geometric version of the proof that doesn't assume.
Yeah, I would like to be able to give you a proof without this assumption. Right. Okay. So maybe I should. Right. So I'll draw a picture similar to what I drew over there. I put CX here, CX here, CX here, like this. So this stop Liouville manifold here, this is X cross F times C with 3 stops. And Knuth tells us that we know about we know what the category of this is. So the wrapped category of this is wrapped category of X cross F across this representation of the A2 proof. And we can, therefore, define this whole phase we're getting by using this loop. That's what I want to do. Yeah, L. And now we need to understand further what happens when we go to this category. These borders are not. Oh, so we'll continue now. This has a functor to W of this guy, where I remove that copy of F. And stock removal says this functor here is the quotient by linking disks of this copy of F, the copy of F that I removed. Linking disks of this, and those are of course the same as they're the linking disks of F inside X times another curve called tau. This is tau. So that's the quotient by these objects. These guys are all orthogonal. Well, they're left orthogonal to these. The image of this is left orthogonal to the things we quotient by, which means the composition is fully faithful. So let me write the Hom from L cos gamma to anything times tau. Kunin tells us that's the Hom from L to this guy times tensor Hom from gamma to tau, and this guy is 0. Okay, so before I erase this, let's note this picture is the same as this picture. Why is it the same? Well, it's not exactly the same, because here I have sort of a Liouville sector type boundary, and here I have a stop. But these are equivalent. You can complete this and add up a stop there, and the category is the same.
So I thought one picture took place in X and the other in W.
Everything is, there's W hasn't really appeared yet. I mean, eventually I'll put it in W. Right. Yeah, so now I think comes W. So, W. So yeah, now here's C, here's the half plane cross X, and now here's our stop, CX plus, and R cross F. So now this hypersurface here should use a different color. This hypersurface, it's a Liouville sector type boundary, it divides W into two pieces. And so I can use the Meyer-Vietaris push-out formula. So this push-out, so it's the push-out of graph category X. So that maps to, so I'll do the outside. The outside here, what is the outside here? The outside is, okay, W, well, it doesn't really matter. It's W, graph category of the Liouville sector, W minus this standard neighborhood. Now, if you really want, you could certainly observe this is, of course, the same thing as W, just with that stop there, Y equals X. Doesn't really matter for what we're going to do right now. The other map is into the category of this piece, which is CX here, CX here, CX here, and then F. Okay, so this push out includes into the route type category W stops along this. If, just an aside, if W were Weinstein, this would be an equivalence. But that assumption isn't relevant for what we're doing now. Right now we just observe this map. Okay, this is the same map as before. This is L maps to L times tau. L maps to L times tau, where tau is this guy over here. And you have the same orthogonality as before. So by having orthogonality, includes fully faithfully into this push out also. Okay, so that's the proof of the proposition.
So what goes wrong if W is Liouville? I mean,
W can be Liouville.
Right, in that last map, that it's not an equivalence.
Just because, well, we need to know some sort of generation result for Liouville manifold, whatever Lagrangians. Actually, in this case, since the thing you're removing is so small, yeah, no, I still don't. I still think we don't know. Right, somehow, so if you have Lagrangians in W, which are disjoint from the blue hypersurface you're cutting along, then they're obviously an image of this map. But if you have some general Lagrangian which passes through the blue guy, you need some sort of argument to show that it's hit.
The blue guy is like toward X, right? You can push off of it. In this particular case,
Since the blue guy is X Weinstein,
Yeah.
you think you can push off?
I mean, because you push off this core.
I'm not sure. Okay, so my corollary is the W X comma F. In particular, embeds fully faithfully in the Rapid category of cotangent bundle stopped. If X embeds the hypersurface in the poster bundle. And from last time, we know this is sheaves with singular support along. Along this guy. Are there any questions about this part of my talk? I'm going to switch to something a little bit different. Yeah.
The singular is copied as like sub-analytic.
Yes, because this equivalence requires some, sub-analytic or whatever your favorite minimal structure is. You can use that one as well. Say containing sub-analytic.
Maybe it's worth making a remark that the stable model, symplectic stable model bundle of your one-state manifold admits of polarization. Then you embed after stabilization, which is good enough.
Okay, so now I'm going to enter the sort of more speculative part of the talk by following Paul's convention that theorem means conjecture, and we won't see that conjecture. So what I want to discuss is what the Cauchy property. So I talked about this Meyer-Vietoris theorem last time. That's somehow the Cauchy property for covers of two guys. What about for covers of n guys? So for that, we need this notion of what I'll call an admissible cover. So let's say X is Liouville manifold. Let's see, so H. So a collection Liouville sectors. It's 1, it's n. It's called admissible if and only if you can choose these transverse Hamiltonian vector fields. Call them X sub II transverse to boundary Xi, such that they're tangent to the boundary of Xj for other UCs. This is some sort of purely symplectic condition. Example.
You're going to see many kinds of can you suppose something utility between them?
Yes, we want that too. That probably doesn't follow from what I know. Yes, and the plus on commute. Thank you. There are a few different equivalent ways of writing this, and so some of them have stronger conditions. So I hope what I've written is sufficient, but there's something one can write here. So example is take any M, this manifold AI are the dimension 0 submanifolds of boundary, and the boundaries are transverse to each other. Boundaries are mutually transverse. The boundary I are mutually transverse. So something like this. Okay, so then this collection T star AI, this is an invisible cover of T star F. So in general, you should think of an invisible cover as somehow giving you cotangent bundle coordinates near the various strata. So on the codimension 1 stratum, so if you look at this cover, if you're near a point where you're just on the boundary of a single one of these xi's, then you have one cotangent bundle coordinate. It's at T star r cross some Liouville manifold. And if you're at a point where k of these guys intersect, then you have coordinates which is like T star to the k times some Liouville manifold. And these boundaries are just when each of the k coordinates equal to 0. So a bunch of k mutually transverse hypersurfaces there. In particular, k is at most half the dimension of x. These intersections of these boundaries are all coisotropic. Okay. So now, remembering what theorem means. So for any Liouville manifold X and this will cover by Liouville sectors for which I sort of have to explain what this means, which every stratum is Weinstein. Following equivalence, Hochulin so it satisfies the Cauchy property for this particular cover. So I should explain what this hypothesis is. Every stratum is Weinstein. So if you have covering by Liouville, this will covering by Liouville sectors, it looks something like this. So stratum is just something like this. Maybe this region, or say this region. Okay, and every stratum, so something like this, this is also of the form R K cross F 2n minus 2k. The dim x is 2n. So where this guy is a Liouville sector. Okay, so every stratum being Weinstein means every F is Weinstein.
I don't understand what so I'm saying this is of the form F times R to the K. Okay, I mean, F is basically what's associated to the intersection of the boundaries.
Yes, it's any stratum of any of these red guys that I drew here is of the form R to the K cross a Liouville sector.
Okay,
So the one you pointed to K is 0.
That's what I want to check.
Yeah, yes, the one I pointed to is K equals 0.
Okay.
This is K equals 1, this is K equals 2.
Yes, thank you.
K is the codimension of the stratum. stratum. So as expected, this is one can reduce this to the case of 2-element covers, as long as one takes X to also be a Liouville sector.
I'm sorry, now that I'm looking at your picture, it becomes even more puzzling what you mean by stratum. So, because the thing that you drew is this short segment that lies on the.
I didn't draw this boundary so well. There's
What I'm trying to say, I'm sorry, you have a little red segment called
Yeah.
labeled K equals 1.
Yes.
Okay? So how is that thing defined? Because it's not the intersection of the boundary of one of them with the other one.
well, so it's the boundary of this guy, and then you remove some other pieces.
Okay.
It's the stuff which is in here and not in here and not in here. It's like any Boolean combination or something like that.
Some kind of inclusion-exclusion used to define it.
Yeah, somehow you take the sort of inside, outside boundary to the sort of
Okay.
index set of your cover. So anything here gives you a stratum. Okay, so now this is sort of obviously some sort of Cauchy property.
All right, let me just pause for a second. When you say that the home to the colimit,
Yep.
it's taken over all these things?
It's
Or is it
no,
just
not
over
well.
one?
You could subdivide and make it like that, but I was just saying
Just over the intersections?
over the intersections.
Okay.
Yeah,
I just
it
want-
means it implies the thing you said. But over the stratum. Yeah, I mean, if you just assume somehow that every intersection was Weinstein, you can't get very far with that because it's not preserved, it doesn't have the right property. Okay, this is obviously some sort of Cauchy property. So ideally, we'd like to define some sort of topology in which objects are Liouville sectors, or maybe Weinstein Liouville sectors, and the coverings are coverings, maybe admissible coverings for which we can define this. So if one just sort of takes what I said at face value, it doesn't really make any sense because you can easily have coverings which don't have common refinements. Just sort of for very, very silly reasons. I mean, take any say cover T star S1 by a bunch of copies of T star of an interval and apply some crazy symplectomorphism to it and get a new cover. They're going to have intersections which are compacted. You're never going to be able to find a common refinement of those two. So instead, right, so to say what, so to get a reasonable Cauchy property and a reasonable topology, we have to make some sort of much more drastic restriction on what sorts of subsets we want to consider. Okay, so one proposal for what these are is the following. So let's say X is, I can just leave open a hole. Okay, so we say U inside X is semi-conic, and only if when you take positive Liouville flow applied to U, it's stabilized by the positive Liouville flow. And
John, when you say every stratum is Weinstein,
Yes.
is it important that they're simultaneously Weinstein?
no, they're somehow, they're completely separate. It's just separate assumption on each one. But I mean, you could make them simultaneously Weinstein, given the assumption that they're all separately Weinstein, just by choosing a nice adapted. Right, so we say X is is separable but only if right. Oh, this is a working definition. So for every semiconic compact K inside the core X, and every collection of every covering of X, every covering of semiconic open subset. So the U alphas are semiconic inside X, and K is contained and they cover K. Okay. Then there exists an admissible covering admissible collection, say V1 through VM, refining this U alpha, so that means every VI is contained in some U alpha and covering K. K is contained in the union of VIs. Okay, so I think that's the definition I want.
Okay, so I'm sorry. When you go for expands or?
It expands.
Then how can it be semiconic?
In the core.
Oh.
Yeah, sorry. So I should say, right. It's yeah, I didn't say VIs are semiconic also. Yeah, VIs are semiconic. VIs and VI semiconic.
The content of things you can make them admissible. Right.
Yes. So admissible is the key. Is the key here. And also you can there's a Weinstein version of this. Weinstein separable is Weinstein admissible. Weinstein admissible meaning all the strata rules. The role of this definition is to be the hypothesis you need to show the Cauchy property. Okay, so then this has even more quotes than that theorem. X is Weinstein separable, then okay, there is a Cauchy of categories on the core of X in the semiconic topology. Given by the sections over U is supposed to be, I have to take the inverse limit over, so remember U is a subset of K, and I need to take the V inside X, semiconic sector W.
you're not done stating the theorem.
Maybe there's the Kirchner, that's a statement.
What else should I
This is
say?
a tautology.
What should I say? What else is missing?
No, more of X goes to W of X.
That follows from this, what I wrote.
Is that true?
Yes.
Because the only thing containing the core is all, because everything.
So why does this theorem have any quotes at all?
I mean, we didn't prove the theorem by rate.
No, I assume that theorem.
Yeah, then it's obvious.
Okay. Oh, I think these are the quotes for sure.
The conditional quote.
Yeah, maybe you're right. Maybe I shouldn't have said this as more quotes. The same number of quotes. Right, so we need, of course, to be able to produce some examples of this. Like this is also has quotes, which is if X is Weinstein separable, then X union any Weinstein handle is also Weinstein separable. So in particular, by induction, any Weinstein manifold is separable. But also, for instance, cotangent bundles are obviously Weinstein separable. You can take arbitrary, find nice covers of the zero sections, taking them. Yeah.
So is this like there exists a core, does there exist a Weinstein structure on the actually Weinstein handle, or like any Weinstein structure?
Oh, right. When I say Weinstein handle, I mean somehow the standard model.
Okay.
I mean,
Good.
you could.
Because I'm just sort of moving in space Weinstein structures, presumably. That's great, thanks for this.
I mean, so I don't say that we can. You don't have to perturb the Weinstein handle. You can attach any Weinstein handle you want. So it could create something. You don't need to make the singularities generic. At least that's the belief so far.
In the way you formulated the definition, is Weinstein separable and apply to Weinstein?
Yes.
Why?
Because if you have a Weinstein admissible covering, you can, the answer to your earlier question, you can glue together, you get a Weinstein.
Yeah, but I mean, like, so you believe, how to say it looks like you have something with singular Lagrangian skeleton that's, which locally is given by some Weinstein function. You believe you can glue those?
No, I mean,
all ways?
I mean, the whole point of this definition is because you can't glue, otherwise this definition is so low.
Then why does it want that the global influence?
So, okay, take K to be the whole core.
Okay.
So, and take U alpha to be anything you want, anything like maybe just one element of the cover. So this says there exists a Weinstein admissible collection of Liouville subsectors, which cover the whole thing. And if you have a Weinstein admissible collection of Liouville sectors, their union is Weinstein.
Okay, maybe we'll discuss that.
So is every Weinstein manifold Weinstein separable? Is that where this is leading?
That's what this proposition says. Yeah. But somehow there are other things too, like cotangent bundles also Weinstein separable. That's obvious, assuming I stated the definition correctly. So then you can get more things, like take a Weinstein manifold and attach Weinstein handles, or take a cotangent bundle and attach Weinstein handles. That gives you, it's just, right, being Weinstein separable is a statement about the specific Liouville vector field you have. If you perturb it, it might change.
So that's the question, is this, do you know this, that you expect this definition to be invariant in the perturbation?
No, of course not, no, there's no, I mean, you could, I mean, yeah, there's no reason to be.
So do I ever need to know the Liouville vector field, or just that there existed some Liouville vector field that made my Weinstein manifold Weinstein separable, and then I could forget about that vector field for the rest of my life?
Well, the vector field tells you the core,
Right.
and that the sheaf is on the core.
You're saying
So-
that I need to prove separability for the vector field giving me the core?
And if that's the core you want to have a sheaf on,
Yeah,
then
yes.
yes.
I mean, a priori, what John has told you the sections are, do require global geometry.
Yeah.
Not just of the core.
Yeah. Okay, so I actually should make a little bit of this definition a little bit more precise. So, open Liouville vector is an ascendant union of Liouville sectors. X is union xi equals 1 to infinity. I mean, these are nested. Okay, and so these guys, these V alpha, these V guys, these are open Liouville sectors, not ordinary Liouville sectors. Right, because if these are semiconic open sets, the semiconic condition is rather incompatible with having smooth, nice boundary. So maybe I can conclude with just giving an example. Example. So let's do T star S1, but with so this is its core is S1, but I want the Liouville vector field which has only 2 zeros here and here, so I build it out of Weinstein handles. So this just goes out like this. Oh wait, is it clear what Liouville structure? Okay, so this is the core. The core is a circle, and I claim this is Weinstein admissible. Well, let's take a look at what some semiconic open sets look like. So of course, one thing I could do is I could take a neighborhood of this this critical point, small ball, but I need to make it semiconic, so I have to flow up. So that would sort of look like, so I take this ball and I flow up, I get this. So these are sort of small semiconic neighborhoods of this critical point of index 1. Okay, and you see their Ralph pi category is simply the Ralph pi category of T star 0, 1. It's perfect C. Now, I want to draw what happens for a slightly different open set. What if I take semiconic neighborhoods of one of these points? So I take the ball down here and I flow it up. I flow it up like this. Okay, and I do not get this cocore. I do not get this cocore. So that's not part of the manifold. So what do I get? So this looks sort of like this. It's a small conic neighborhoods of this point P. And you see, it looks like we're getting a half plane. The half plane vanishes, so that's not what we want. That's bad. But the point is, though, we should remember that there's this one Liouville trajectory out of P which doesn't go to infinity. And so at that one, we should put a stop. Right, and now this guy, so this is now an open Liouville sector. You should think of it now as this ascending union of these guys. So here's one Liouville sector, here's a bigger Liouville sector containing it like this, but somehow they never include this point at their boundary infinity. Yeah, and then the other example, okay, is what happens when you take a point, take a semi-conic neighborhood of this point. Well, now sort of as a Liouville manifold, it's C, but as you go around and follow the Liouville vector field up here, you see that there are two stops. There are 2 points on that boundary infinity of C which don't go to the boundary infinity. Oh, so I think I'm out of time.
Are there any questions?
So the direct kind of category of open Liouville sector is a direct limit of the, like,
Yes.
along all subsectors?
Yeah, and I should have said, sorry,
Under the including the post that is that direct limit.
there's only one, I mean,
Yeah.
there's only,
And then that automatically kind of includes these fictitious stops. Okay, because the
Yeah,
rate
because-
definition for the kind of category of any semi-conic section.
sorry. Yeah, so, right, so one has to say what exactly one means by these admissible semicon, how you make them. So somehow, you don't want them simply as exact symplectic manifolds. You have to remember what part of their boundary infinity hits the boundary infinity of X, and only use those Lagrangians.
With extra data.
Yeah, so somehow an open Liouville sector really, right. So this is somehow the quick and dirty definition of the open Liouville sector. The better definition is it's just it's a pair, exact symplectic manifold, comma, contact manifold, and embedded near infinity, and that's where you can go to infinity. You really don't want to remember somehow this particular exhaustion. It's a property that exists in exhaustion by Liouville sectors.
Any other questions? So when you did in this example, you just said there is a stop at infinity. Couldn't you just do the same thing here, that somehow the boundaries of the xi would converge to some stop at infinity for x, and that's the data that you would have?
Sorry, which things converge?
The part, so xi's have boundaries, right?
Yes.
So at infinity they would converge to something.
Well, that point at infinity, that stop, you shouldn't think of it at all. It's not bad. You have this other, the part that you care about, the part that Lagrangians can go to, and this other part that it doesn't converge to anything.
You're not allowed to go to it.
Yeah.
The other part is the union of the boundaries at infinity of the x's.
Okay. I guess if there's no more questions, then we should thank John again.